In this session, we're going to see more asymptotes. More than what? More than the vertical asymptotes that we found in a previous video. We're going to start off by looking at the graphs of three functions. And what I want you to know from these pictures is basically the vocabulary we're looking at. The first graph is the graph of the function y equals 1 over x, that familiar guy, the reciprocal function. As we saw in the previous video, there's a vertical asymptote on the y-axis. I'm not here to talk about that right now. There's a horizontal asymptote along the x-axis. Now that's one of the asymptotes we're going to be finding. And we'll see how to do that in this video. The second graph is the graph of y equals 5x plus 2 over 2x plus 1. I don't want you to get wrapped up in that. What I want you to see with this one is that it has a horizontal asymptote that is not the x-axis. The third graph is the graph of y equals x squared plus x minus 4 over x minus 3. I again don't want you to get wrapped up in that. What I want you to see with this one is that the asymptote that is governing the shape of at least part of the graph is not horizontal. It's actually called an oblique or a slant asymptote, depending on the author. Now, what's going to determine for us whether we have a horizontal asymptote on the x-axis or a horizontal asymptote that's not the x-axis or an oblique asymptote is actually how the degree of the numerator compares to the degree of the denominator. In the case of y equals 1 over x, the degree of the numerator is smaller than the degree of the denominator. Remember that a constant has degree 0, x has degree 1, and so 0 is smaller than 1. In the case of the second graph, the degree of the numerator is 1, 5x plus 2. The degree of the denominator is also 1, and so we have matching degrees. When that's the case, it's actually the leading coefficients that we're going to care about. Here with 5x plus 2 over 2x plus 1, 5 over 2 is 2.5, and that's actually where this horizontal asymptote exists. It's y equals 2.5. For the third function that we're looking at, x squared plus x plus 4 is degree 2 in the numerator, and in the denominator, x plus 3, is degree 1, and so what we have is the degree of the numerator is bigger than the degree of the denominator. And if they differ by 1, as they do here, then we end up with that slant asymptote. Let's recap. In general, a rational function has a polynomial numerator and a polynomial denominator. If the degree of the numerator is smaller than the degree of the denominator, then we're going to have a horizontal asymptote that is the x-axis that has an equation y equals 0 every single time. If the degree of the numerator is the same as the degree of the denominator, then we still have a horizontal asymptote, but now all of a sudden it's y equals the ratio of leading coefficients. And that's what we saw in the second graph. The leading coefficients were 5 and 2. That ratio is 2.5. And that's where this horizontal asymptote exists, y equals 2.5. If we have a degree in the numerator that is bigger than the degree of the denominator, and if they differ by 1, then what we have is an oblique asymptote, also called a slant asymptote, and it's actually going to be the case that it's y equals the quotient from what we get by performing long division. I know it kind of sucks. Here's what else sucks. I don't like to tell folks, if you have this situation, do this. If you have that situation, do that. In this other situation, then you do this. But they didn't ask me my opinion on this stuff, and so I just have to tell you it like it is. So to make a long story interminable and to recap the recap, If the degree of the denominator is bigger, y equals 0, horizontal asymptote. If the degrees match, it's a ratio of leading coefficients. Y equals that number, so it's horizontal asymptote. If the degree of the numerator is bigger by 1, then we have y equals the quotient, and that's the slant asymptote. And while the graph of a rational function can have more than one vertical asymptote, as we saw in a different video, they'll never have more than one of these critters. So it's just up to us to figure out which one it is and what it is. And that's exactly what we're going to do in our examples. But before we get to them, I would be remiss if I didn't say what an asymptote actually is. Informally, an asymptote is a line that governs the behavior of a graph. And we can see that indicated in our example functions here. In y equals 1 over x, the horizontal asymptote governs part of the behavior of that graph. The vertical asymptote governs part of the behavior of that graph. And let's skip over here to the one with the oblique or slant asymptote. We have that asymptote, and then as you can see, there's also would be a vertical asymptote. And those are just lines, as I said, that govern the behavior of a graph. Now to our examples. For our first example, find the horizontal or slant oblique asymptote of the function f of x is equal to 2x plus 1 over x minus 3. The numerator is degree 1. The denominator is degree 1. Because those numbers match, we're going to look at the ratio of leading coefficients. 2x plus 1 the numerator, 1x minus 3 if you will the denominator. So here we have a horizontal asymptote of y equals 2. Yep, that's it. Don't worry, it all comes together in another video. Next, same instructions. The function is f of x is equal to 2x squared plus x minus 8 over x squared minus 4. The degree of the numerator is 2. The degree of the denominator is 2. What's important is that they match. And in that case, we're looking at the ratio of leading coefficients, which again is going to give us a horizontal asymptote of y equals 2, because that's the fraction composed of the leading coefficients. Next we have h of x is equal to negative 2 over x plus 1. The degree of the numerator is 0, because that's the degree of a constant. The degree of the denominator is 1. That makes the degree of the denominator bigger, and as you may recall, that means we have a horizontal asymptote of y equals 0. Next, same instructions, but our function is r of x is equal to x squared minus 4x minus 5 over x minus 3. X squared minus 4x minus 5, the numerator is degree 2, that polynomial. The denominator, x minus 3, has a degree 1. So the degree of the numerator is bigger by 1. As you may recall, that means we're going to find the quotient using long division. So x squared minus 4x minus 5 divided by x minus 3 is what we're looking at. And let's whip through some long division here. Actually, I want you to pause the video, practice your long division, and then hit play. Okay, so after performing the steps of long division, I have an answer of x minus 1 minus 5 over x minus 3. Quotient plus remainder over divisor. I said it was y equals the quotient. The quotient is x minus 1. So we have an asymptote of y equals x minus 1, which is a line with a y-intercept of 0, negative 1. To tidy this up, we would say we have an oblique asymptote or slant asymptote. I don't really care which of those two you use, but use one of them. It's y equals x minus 1. We get to dump the remainder. Doesn't that feel good? Okay, I know the question that's burning on your mind. What if the degree of the numerator is more than 1 bigger than the degree of the denominator. All right, fine. Let's suppose we have a rational function. Say r of x is equal to x cubed plus 3x squared minus 3 over x plus 3. We would do the same thing. It's going to be y equals the quotient. Long division. Let's see what happens with some long division. So that was the quickest division you ever saw. I have an answer of x squared minus 3 over x plus 3. And as we said a minute ago, it's y equals the quotient, which does not include the remainder. So y equals x squared is what we end up with. That is a parabola. I can't call it an asymptote because by definition an asymptote is a line. So this is actually like a parabolic guiding force. But let's not get too wrapped up in that right now. It's just sometimes people ask me what happens in situations like this.